Okay, so this next part, we're gonna not veer away from numbers entirely, but we're gonna talk about some kind of theoretical and research design-ish stuff for a few sections, and then we'll come back to doing what you would more traditionally think of as math, as statistics. The reason this is important, though, is that when you're gathering data, the data that you work with, any answers that you get from those data are only as good as your sampling methods. They're only as good as your research methods. If you gather data incorrectly, if you gather biased data, which we'll talk more about what bias means, if you don't gather it in a logical, structured way, then it doesn't matter what you find. You're just playing with random numbers. If the data aren't good, then just doesn't work, right? So we are going to talk a little bit here about different types of sampling. Then we'll talk about research design, and then we'll talk about ethics in the next couple sections. So to start, we already mentioned in the very first section that sampling means picking a smaller group of individuals from a population that you're going to gather data from. And this could be humans, this could be animals, this could be I don't know. It could be businesses, like whatever the thing is that you're studying. Like I said, hot dogs, it doesn't matter. But it's picking a smaller group from the overall population. When you sample, there are different ways to do it. One way is called convenience sampling. So you'll see that's the thing here, right? So convenience sampling, that is what it sounds like. It's just convenient. Sample whoever's there. We would rather, as researchers, use random sampling, and I'll come back to why. But random sampling is generally considered better than convenience sampling. And there are several different kinds of random sampling that I'll go over. Um, Another important thing about sampling to think about is whether you're sampling with or without replacement, which that'll come back up when we talk about probability in a little while later in this course. Sampling without replacement basically means that once you have been chosen for a sample, you cannot be chosen again. That's what we usually would think of as being logical, right? If you're in a third grade class and they're picking line leaders and they pick the first line leader, you can't get chosen as the second line leader. That doesn't make sense. You need two different humans. Okay, but theoretically, in statistics, you might want to do sampling with replacement where you put the individual chosen back in. Okay, and we'll talk about what the implications are for those different types of sampling with or without replacement, as well as convenience versus the different types of random sampling. So, convenience sampling, I'm not going to go over much more because convenience sampling is just like I said, it's you get who you can get most easily. Random sampling, when we say random, random means that every individual in the population has an equal chance of being chosen. Every individual in the population has an equal chance of being chosen. So that means that in order to do random sampling, first, you would need a list of every individual in a population, every single one. Then you would need to like assign sequential numbers or something like that and use a random number generator to identify individuals. Or maybe you have every individual in a population, you write their name or a code that represents them on a slip of paper, and maybe you have a big enough hat to put all those slips of papers in and you shake it up real good and you draw one, you shake it up again and you draw one. That would also be random sampling, right? It's every single individual has an equal chance of being chosen. If it's real simple random sampling, that means you're doing it with replacement. Because otherwise, after you've chosen the first person, the next person, like, not everybody has an equal chance. That first person you chose no longer has the same chance of being added to the sample because they're already there. So, real random sampling is with replacement. We'll come back to the theory versus reality, though. I should say theoretical random sampling is with replacement. So the random part here is that you're randomly selecting individuals out of the whole population. The next kind of random sampling we'll go over here is stratified sampling. So a strata basically means like a layer of something. It's a group that's a particular layer for some variable relevant to the group. So maybe you have maybe you have a high school and you're trying to do some kind of poll to see how the new, I don't know, disciplinary code for the high school is impacting students and whether or not they're satisfied with it. So you might look at the ninth graders, 10th graders, 11th graders, and 12th graders, and you might say, okay, I want to get an equal number of kids from each grade level and get their opinions. So I will randomly sample 25 ninth graders, 25 10th graders, 25 11th graders, 25 12th graders. Or maybe you're at a school that has kind of a higher drop rate, and so maybe you might want to keep it equal. Maybe you have more ninth graders and fewer 12th graders, so you would want to keep it proportionate, and you would want to sample more ninth graders than 12th graders. Either way, if you've divided the whole population of students into ninth, 10th, 11th, 12th, and then you're doing the sampling specifically out of one of those grade levels at a time, that makes it stratified instead of simple random sampling because you're not randomly sampling individuals from the population, you're randomly sampling individuals from groups that you identified in the population. Okay, so stratified, you've got groups and you're sampling individuals from within them. Cluster sampling also starts with groups, but you don't sample from within the groups, you sample the actual groups. So you've got your population, you chunk it into relevant groups, you chunk it into clusters, and then you would use simple random sampling, but you would choose a cluster, not an individual, and then every individual from that cluster comes to this to the sample. Okay, so now the random selection isn't of individuals. The random selection is groups out of the population. So again, simple random sampling, you're randomly sampling individuals out of a population. Stratified, it's individuals out of groups, usually because you want to control the numbers from the different groups. Here for cluster sampling, it's groups out of a population. Maybe just because it's easier sometimes when you have groups of individuals together for something. Like if you wanted to study employees in a large corporation, then maybe you would want to only pick specific stores and then survey everyone in those stores for employee satisfaction or something, so that you don't have to go to every single store. So that's cluster sampling. The fourth kind of random sampling that we're going to talk about briefly here is systematic. So here you start with a preset list. It's in a particular order. And then the random part is you pick a random starting place. Like you might use a random number generator to do this, and you pick a random starting place. And then from there, depending on how many people you want, you would take every nth person. Now you'll see n used a lot in statistics. It just means the number. So it could be every fourth person if you want a quarter of the population involved. It could be every fifth person if you want a 20th of the population. It could be every 100th person if you only want 1% of the population. Whatever it is, the random part is who gets chosen as the first person. And then everything else after that is preset based on the order of the list. Okay, so those are all different forms of random sampling. I mentioned I would come back to this. So the replacement piece, again, it impacts whether or not we can say it's truly random sampling, because if we do sampling without replacement, that impacts probability of being chosen for the sample again. So when you're doing sampling with replacement, you put the person or hot dog or whatever back into the population where they can be chosen again before you draw the next individual for the sample, which means the total population stays the same. That means if you're trying to figure out the probability of somebody being chosen, each individual's probability is 1 divided by n, whatever that proportion gives you. And that stays consistent the whole time. So every individual has an equal chance of being chosen. Sampling without replacement, again, this is often more logical. But if you're not putting an individual back in, that means, so like say you have a deck of cards with 32 cards in it and you sample one card. Okay, now you only have a deck with 51 cards in it. So now instead of a 1 in 52 chance of being chosen, 51 of the cards have a 1 in 51 chance and one has a 0 out of 51 or 0 out of anything chance, right? So it messes with the probabilities. So when we say random sampling, often we're doing it without replacement because it doesn't make sense to have the same individual in a sample multiple times, but theoretically it should be with. Okay. So quick example here. Let me get this set up. Boom, boom, boom. Let's see how efficiently I can do this. Ah, my face is bigger now. Okay, so I just wanted to real quick show you a drawing version of that sampling with and without replacement because I think it makes more sense. So let's say that you have, let's say that you have a bag of marbles, 10 marbles, because it doesn't really matter for this example. Okay, the mirroring is messing with me on here. All right, so you've got a bag of marbles and you start out, oh, there goes my marker cap, and you've got five that are blue and five that are black. So here, if we randomly select a marble, there is a 5 out of 10 chance that the first one is going to be blue. Okay? So I draw my first marble. My first one is going to be, okay, cool. My first one is going to be blue. If I'm sampling with replacement, I put this marble back in the bag. It's a theoretical marble in the sample, and I put the marble back in the bag. So I still have this. So that means that for the second slot, I still have a 5 out of 10 chance if I'm doing with replacement. However, if I'm doing without replacement, now I only have a 4 out of 9 chance. So this dropped because I took one of the blue marbles out, and this dropped because I took any of the marbles out. Let's say on the second draw, you end up with a black marble. Now, for the next draw, for draw number 3, if you're doing with replacement, the chances of the next marble being blue are still 5 out of 10 because we have put both of these back. But if you're doing without replacement, now the chances have gone to 4 out of 8 because we took a marble out, so it went down to 8, but it was not blue, so it stayed the same. So you can see these are shifting, these are not. Without, you see a shift in the probability of being drawn. With, you don't see that same shift in probability. Okay, so that's the with versus without replacement thing. And again, because randomness has, the definition of randomness has to do with probability. Yeah. Okay, so let's see, let's get back to the other screen. Alrighty. So why is all of this important? In order to understand why all of this is important, we need to understand these concepts of variation, error, and bias. So, variation, differences in data, those are normal. We need variation. We said that a variable is a characteristic that can be measured for every individual in a population. Well, a variable says right in the name it has to vary. Otherwise, it's called a constant. And it doesn't, we're not going to measure something that's exactly the same in the whole population. Like you're not going to get a population of humans or a sample of humans and then measure whether or not they're human because the answer is yes the whole time because it's a population of humans, right? So variation is normal. We want variation in data or it's real boring. Um, and when we are sampling, when we're pulling a smaller group from a population, it's always going to be a little bit different from the whole population. Like the idea of pulling a sample, if you have 10 people in a room and you pull 3 individuals from that room, those 3 individuals are never going to perfectly match the 10 individuals. It's just not a thing. You can, with big samples out of big populations, you can have stuff get pretty close, but it's always going to, there's always going to be little differences. There's always going to be variation between a sample and a population, and there should always be variability, variation within any data. That's normal. When we see the term error in statistics, because that term will come up a couple of times in the course, when we see the term error, if we're thinking about just how we use that word in English, we might think mistake, but that's not actually what error means in statistics. Error just means it's different from what was expected. The amount of error means the amount of difference between where we expected something to fall and where it actually falls. So if we're talking about a sample and a population where we expect that's the population, whatever the population is, that's what we're aiming for. Where the actual sample falls, it's going to be a little bit off. And the distance between those is the error. Some error is normal. It would be really weird to get a perfect sample every time. If you get a perfect sample with no error between that and the population every time, that means you're an unethical researcher and you're cheating, or you're doing theoretical mathematics, and that's fine. But error is normal. Variation is normal. Variability in data is necessary. Error does not mean mistake and does not necessarily mean problem. It just means difference. There are different types of error that you might see referred to. Sampling error is the thing that we're trying to avoid as much of as we can when we use random sampling techniques. Sampling error means that it's differences between the sample and the population that are caused by the sampling procedure itself. And then non-sampling error might be other stuff like if you're a biologist and you're studying little tiny frogs and you have a measurement tool that is consistently off by zero point 0.1 milligrams or whatever. Um, Maybe zero point 0.1 grams is more realistic. So if you have something like that where you have a tool that's a little bit off and it's messing with things, that's non-sampling error, right? So faulty tools would be non-sampling error. The way that we do the sampling causing differences between a sample and population, that's sampling error. And if for either sampling error or non-sampling error, if you end up with systematic differences um, that end up misrepresenting things that are like more of a difference than we consider scientifically acceptable, which we'll come back to what that means later too, then that's bias. Bias in general means that some information is being weighed more heavily than other information. So if there's something that makes your data shift in a particular direction that messes with your outcomes, that's bias, and that's an issue. Okay, so random sampling theoretically is supposed to help us reduce bias. And if you have less bias, less risk of error, and less bias, then you have a more generalizable sample, meaning your sample can be assumed to generalize to and represent the population pretty decently. Okay, so again, bias means that some information is considered more than other information. Generalizable means that a sample is a good match for a population it's drawn from. And so a biased sample would be when the important characteristics are mismatched. So let's say, for example, that you are trying to study how adults respond to stress. I don't know. If you do a research study and you say that you are trying to figure out how adults respond to stress, but then the sample you use is all college students because you're a university professor doing this study on stress, that means there is probably bias in your results. There's something wonky in there with the sampling because college students are not a typical representation of all adults. College students tend to be younger on average, tend to experience different stressors because the academic stressors are their own thing. Like there's a lot of differences there. So that would be a biased sample, right? Or if you say you have access to a population or you know like where average stress levels should be in a population based on prior studies, and you gather sample data and you get their average stress levels and realize those stress levels are really low in comparison to what you're supposed to expect. That might tell you there's something funky about either your measurement tool or the sampling you did that resulted in skewed data that's falsely depressed. And that would be or either either it's falsely depressed or they really are not stressed, in which case those aren't the people you want in your stress study. You want a range, right? So anyway, uh, less bias means more generalizability. Error happens, error is normal, but too much error in a systematic direction creates bias and reduces generalizability. So the thing is, like I said, we would love to use random sampling as researchers because random sampling is less biased than non-random sampling. So the least biased, most generalizable samples would come from random sampling with replacement. So you put people back in or individuals from the population back in before sampling the next time. And you would also want perfect participant response rate. So every single individual who gets asked to be part of a study is in it. Realistically speaking, you rarely have access to an entire population. It's really rare unless you're doing very small in-house specific research. Like if you're at Harbor College doing a study of the students at Harbor College, then sure, you can get like school records data for everybody. Cool. Even that's going to have some missing data though. Right? And sampling with replacement is not practical. You don't want to include the same student twice if you are choosing a sample of students, right? You don't want the same person twice answering. So it doesn't make sense, even if theoretically it keeps the probability stable. And you might ask somebody to participate, but they might not do it if they have to actually opt in, if it's not just based on prior records. So there's a big gap between theoretically what we should be doing and what we can do realistically. And so, as researchers, if you go into research, all you can really do is kind of do your best. Like, if you have access to a large chunk of the population you're interested in, you use the most random sampling that you can. You try to do things to get a high response rate so that anybody you do invite participates so that you're not like, losing a particular chunk of the population. And then the other thing that we always do in research studies now is we report important demographics. So we report things that we know are likely to change people's life experiences in a big broad way, things like age, gender, race, ethnicity, socioeconomic status. So we report those things for the samples that we have. And then we also report average levels of whatever our important variables are that we're measuring. Because if we do that and somebody else comes along and they do the same study that we did and they get really different results, the first thing that they can do is go and see, well, did this sample that I used have any really big differences from the sample that they used? Was it a different demographic group? Did they have significantly different levels of whatever the thing was that you're studying to begin with? And then that allows people to kind of figure out what's the effect of the variables that you're actually trying to look at and what's the effect of any potential bias or differences between the ways that the studies were conducted. Okay, so that is the end of this bit on sampling and variability. Again, variability is normal. Error is also normal, and error does not mean mistake. But when error is systematic and in a particular direction, it makes things biased and not as generalizable. Random sampling is one way that we try to reduce bias and increase generalizability. All right.